Right. I guess people are a little late today. Or is it that people have dropped the course because of the midterm? I haven't yet looked at your midterm, but I did post the solutions a few minutes ago. I forgot to put the link to it. Actually, they were on the website, but I forgot to put a link. So you should be able to see them now. So, any questions about the last lecture, which we can take before other people join? I mean, I'll review it, but if there are any specific questions. Because people are quiet. Can you guys hear me?
Yes.
Okay.
Yes.
It's hard. Yeah. It's hard to keep things interactive and with these Zoom meetings, but if you guys speak up once in a while, it'll help. Okay. So let's actually briefly review what we talked about last time. So we looked at the problem with inequality constraints. So optimization with both equality and inequality constraints thrown in, right? And a key, a key concept, I guess, in terms of inequality constraints is, or when we look at inequality constraints, is whether the inequality constraints are active or not. So if they're inactive, basically, they don't really matter in terms of developing necessary conditions for optimization. And we gave some intuition for that. So inactive means that the inequality constraint is strict. I mean, the GJX is strictly less than 0. Okay, and so and then one of the intuition for that was, if you have an inequality constraint that's not strict, then the corresponding X star is sitting inside the interior of the constraint set. And so if it's sitting in the interior, then all directions are feasible. And so the gradient being 0 is not going to be affected by the constraint. Right? So that was the intuition. And then we actually proved that more formally in a result called the KKT theorem. Okay. Also, important to note that the definition of regularity in the case of these inequality constraint problems, you only need to make sure that the gradients of the H's and the GJs that are in the active set are linearly independent. Okay, and the important thing about inequality constraints is, of course, that the mu j is strictly is non-negative. All right, and then let's get to the statement of the. So we proved this by essentially converting the inequality constraints to equality constraints through the addition of these auxiliary variables. And then we'll get to the final statement of the results, which is here. Okay, see, this was the KKT necessary conditions that if X star is a local minimum of ICP, and X star is regular, which means these guys are Li, then there exists unique Lagrange multipliers lambda and mu, such that the gradient of the Lagrangian function at X star lambda and mu is equal to 0. The mu j's are non-negative. Lambdas could be either positive or negative, or 0 even. And mu j is 0 for everything that's not active, right? And then if you look at second order conditions with twice differentiable continuous functions, you get this condition like a positive semi-definiteness condition on this set of y's for which you have these orthogonality conditions. Okay, similar to the Lagrange multiplier theorem we proved for equality constraints before. And if you can also get sufficiency conditions if these mu j's are positive, strictly positive for j in the active set, and there's a positive definite, not positive semi-definiteness, positive definiteness condition on the Hessian like this. Then x star is a strict local minimum of ICP. Okay, so this is where we stopped last time. So in today's lecture, we're going to apply this result to some examples. Okay, so, but actually before we get to that, I'm sorry, I need to drink some tea, I guess. Before we get to that result, there was a question last time about the intuition for why the Lagrange multipliers corresponding to inequality constraints have to be non-negative for J in the active set. Okay, so let's actually give some intuition. So there's a picture in the book, but that kind of tries to illustrate this idea. But actually, I decided that that picture was not completely accurate because it kind of shows a constraint set that's convex, whereas this result holds more generally. So there's another way to look at it. This is also discussed in the book, but not highlighted so much, is just through the use of the sensitivity result that we proved in, was it like, which lecture was that? Lecture 12, maybe. Let's go look at lecture 12. Yeah, sensitivity analysis. So we showed in this lecture that if you look at equality constraints and you perturb your equality constraint from 0 to some u, then the optimum value at the new constraint optimization problem, f of x star of u, is given, it can be written as f of x star minus lambda transpose u. So if you look at the change, or the rate of change of the optimum value, that rate of change is the negative of the Lagrange multiplier, right? That's what we proved. So we actually use that idea to show why mu j's have to be non-negative. To at least argue why, because we proved it, but I just wanted to give some intuition why. So if the jth constraint, Gj, is relaxed from 0, I'm relaxing it by adding, say, making it Uj's for some small Uj positive. Okay. If I do that, if I make my constraint set larger, then if I look at the optimum value, you can't say this with the equality constraints, but with inequality constraints, what happens to the optimum value? I claim that the optimum value with the relaxed constraint is actually going to be smaller than the optimum value without the relaxation. Why is that? Anyone? So I'm optimizing over set, right? This constraint set, Gj less than or equal to 0. But instead of making a Gj less than or equal to 0, I'm going to make a Gj less than, say, 0.1. So now basically I'm allowing for more x's to be inside this constraint set. So if I'm allowing more x's, then I can only improve my optimum value, right? I cannot make it worse, because I can, if by making it larger, some x's actually produce a worse value of fx, I'll just ignore them. I'll just use the ones that were originally in the constraint set with 0 instead of uj. So enlarging the constraint set will always improve the optimization, optimum value, right? So this is true, but this won't be true for equality constraints, because if you perturb an equality constraint, you're now making the constraint over a different set that doesn't include the original equality constraint. Okay, so you're not really enhancing or enlarging the constraint set by doing that. But for inequality constraints, by perturbing the inequality constraint in a positive direction, you're going to actually enlarge the constraint set, and so the optimum value will be smaller. Does that make sense to everyone? So as optimization is over a larger set, so the optimum value cannot be larger, but it can only be equal or smaller. Now, since J belongs to the active set, then we know that Gj of x star is actually 0. And if you, for small enough uj, okay, so we can think of this as it's still like an equality constraint. So again, this is intuition, it's not a proof, but this is the intuition. So we can think of this, the perturbation uj as the perturbation to an equality constraint. But we know that by the sensitivity interpretation of Lagrange multipliers for equality constraints, that f of x star at uj should be f of x star minus the Lagrange multiplier times uj plus little o of uj. So this was the result from lecture 12, right? So this result. Okay, there we actually perturbed all the u's, but suppose we just perturbed uj, then this guy would be just replaced by lambda I times lambda j times uj. So this here, of course, now we are considering an inequality constraint that's active, so that we have a mu j here instead, right? So it's mu j times uj. So now if we rewrite this, you see that minus mu j uj equals f of x star of uj minus f of x star. Okay. Actually, you can maybe put the little o of uj on this side. It doesn't matter where you put it. Okay. Let's put the little o of uj here on the left-hand side. And so this is less than 0. The right-hand side we know is less than 0, less than or equal to 0 by this result here, right? But now I just divide by uj and let uj go to 0. And that if you do that, basically the right-hand side is non-negative. Not positive. So minus mu j is not positive, so mu j is non-negative. Okay, makes sense? All right. Any questions? So this is kind of intuition why with inequality constraints, you have a non-negative Lagrange multiplier. Okay. Now, remember the condition for active constraints for all j in the active set, right? Mu j is 0, right? So we proved that. So another way to write this, as I was kind of briefly mentioned last time, you can think of this as mu j is 0 whenever you're in the active set. Right, today I keep doing this. I meant to say the exact opposite. Okay, so j is not in the active set. Right? If j is not in the active set, mu j is 0. We know. If j is in the active set, the mu j will either be positive or it could be 0, but it's not going to always equal 0, right? So if you're not in the active set, then that constraint is not going to be important. So mu j is 0. So mu j is 0 whenever you're not in the active set, but that means whenever this inequality is strict. Right? So that means mu j is 0 whenever gj of x star is not 0. Right? The constraint's not active. So you're inside. Okay, that means if I look at the product of mu j and gj at x star, that product has to be 0 always for all j. Because for the active ones, gj is 0. For the inactive ones, mu j is 0. The product is always 0. So this is another way to write the statement. This statement, mu j is 0 for j not in the active set, is equivalent to writing this way. And writing this way is called complementary slackness. Okay, so often you'll see in the KKT theorem, rather than writing, where is our KKT theorem? The KKT theorem, rather than writing mu j is equal to 0 for all j not in the active set, you would replace this by a statement like mu j. You replace this is equivalent to mu j gj of x star equal to 0. Okay, so that's how you will see the statement written. Okay, so that's called complementary slackness. Any questions about that? Okay, so now let's do an example. All right, so this is an example to illustrate that applying the KKT theorem to solve, to explicitly solve, not numerically, but explicitly solve analytically an optimization problem with the inequality constraints is a lot harder than applying the Lagrange multiplier theorem. Okay, and we'll see why now. All right, so we have this seemingly reasonable problem. We have a quadratic function like this, and we have two constraints, two inequality constraints. One is quadratic, one is linear. Okay, so the function is this, and the constraint can be written as x, this minus 5, g2 is this minus 6. Okay, so let's say we want to apply the necessary conditions to identify potential local minima, just like we did with the Lagrange multiplier theorem for equality constraints. Okay. So what are the first order necessary conditions? First of all, I mean, we have to meet the constraints. So that's the function, the thing has to be feasible, my x. So we'll look at, so by the way, I'm not going to put a star, throughout because I have squares and things like that. So I'll put the star on the x at the end after we have solved after we have some potential solutions for the minimum. We'll call those solutions x star. But before we get there, I know when we talk about the LMT, we put stars throughout, but it gets a little cumbersome. So I'm going to drop the stars until the end on the x. Okay. Actually, the book puts stars also on the mu's and the lambdas, which I think is a little redundant because the mu and the lambdas really don't correspond to any optimum value for the function. So it's x that's being, those are auxiliary variables. You can think of it as that way, and x is the variable that you're optimizing over. So putting a star on x makes sense. Putting a star on the mu's doesn't make much sense, in my opinion. Okay, so it has to satisfy the constraints. So the constraint g2x less than 0. It has to satisfy the Lagrange multiplier, the Lagrangian gradient equal to 0. And the Lagrangian gradient is, there are two constraints. Forgot to put the gradient again on the G. I don't know why I keep doing that. Gradient G1, mu2, gradient G2x. So this has to equal 0. In addition to that, we know that mu1 has to be non-negative, mu2 has to be non-negative. And finally, we have the complementary slackness conditions, which I'll write this way. Mu1 G1 x must equal 0, mu2 G2x must equal 0. It's another way of saying that the mu's are going to be 0 when I'm outside, when I'm not active, when I'm strictly inside the constraints. Okay, so the difficulty here in solving solving these equations to identify x and the corresponding mu's in this case, or the x star and the corresponding mu, is that you don't know beforehand which constraints are going to be active and which are not going to be active at x star, because you don't know what x star is until you solve these equations, right? So it's like a chicken and egg problem, right? So what do you do then? Well, what do you have to do pretty much, although in some cases you can simplify things depending on the kinds of constraints that you have, but in general, unless the constraints depend on individual variables or something like that, where you can get some simplification, you have to actually consider all possibilities. So that's why this is difficult, right? Much more difficult than the equality constraint problem. So you need to check for all possibilities. For constraint 1 being active, constraint 1 being inactive, constraint 2 being active, constraint 2 being inactive. Those are 4 possibilities in this case. But if there are m constraints or r constraints, you'll have 2 to the r possibilities that you need to check. So it can get cumbersome very quickly. Right? All right, but let's, at least for these simple examples, we should be able to do it. But one other thing that we need to keep in mind when we look for solutions, candidate solutions for the minima, is that those x star have to be at regular, right? So to check that regularity, we need to look at the gradients of the g's and make sure that the gradients of the g's are linearly independent for only the active constraints, right? Because these are both inequality constraints. So regularity is, you need to check linear independence only for the active constraints. But let's look at the gradient of g. The gradient of g in this case is easy, 2x1, 2x2, and gradient g2 is 3 and 1, okay? Now, you can't say at the outset that these two vectors are going to be always linearly independent, right? Why is that?
We don't know x1 and x2.
It depends on x1 and x2. So anyone want to give me a choice for x1 and x2 for which these two will be linearly dependent?
x1 1.5, x2 0.5.
Very good. So if x1 is 1.5 and x2 is 0.5 or half, then G1, a gradient of G1 and gradient of G2 are going to be equal to each other. So you can't say at the outset that for all x, you're going to have regular no matter which constraints are active. So it'll really depend on which constraints are active, right? And what the value of x star is. Okay, so now let's investigate. Let's do the case where the first is inactive and but actually both are inactive in this case. Case 1, 0, 0, in other words. Inactive, inactive. Mu1 equal to mu2 equal to 0. So in that case, the Lagrangian condition, the gradient of Lagrangian being 0 corresponds to the gradient of f being 0, right? So it's like interior for both the constraints, basically. So the gradient of f being 0 is, let's put down the equations for that. Gradient is easy to calculate. It's just, you know, the gradient of this with respect to, the derivative with respect to x1 is 4x1 plus 2x2, and with respect to minus 10. And with respect to x2 is 2x2 plus 2x1 minus 10. So let's write that down. 4x1 plus 2x2 minus 10 equal to 0 for the first component of the gradient. Second component of the gradient, 2x1 plus 2x2 minus 10 equal to 0. Simplify this, you get 2x1 plus x2 equal 5, x1 plus x2 equal 5. Solve this with a solution.
x1 is 0, x2 is 5.
x1 equal to 0, x2 is equal to 5. Okay, good. So we need to now see if this is actually a valid solution. So can both constraints be inactive? That's the question. So let's plug in. So they have to meet the constraints, right? This choice of x has to meet the constraints. Okay, so let's see. And of course, not just meet the constraints, but it also has to meet the complementary slackness condition. But let's check the constraint first. Well, actually, no. In this case, for this case, you don't have to worry about complementary slackness because you already know that the mu1 and mu2 are both 0. So in this setting, mu1 and mu2 are both 0. So this will be satisfied automatically. So let's just look at these constraints. So x1 squared plus x2 squared less than 5. So if you look at x1 squared plus x2 squared, and that's 25, but that's not less than or equal to 5. Okay. And it turns out that the second constraint is met, 3x1 plus x2 is 5 in this case, which is less than 6, but the first one's not met. So this solution is not feasible. So we have to move on. Okay. All right, so now let's make the first one inactive and the second one active. In this case, mu1 is 0, but mu2 is non-negative. That's all we know. Mu1 is equal to 0. Okay, so now if we look at the gradient condition, that will involve mu2, but not mu1. So let's write down the gradient. The gradient of f is the same, 4x1 plus 2x2 minus 10. And then the gradient of G2 was 3. So you just get, well, the first component was 3, so you get 3 mu2. And then the second equation plus 2 equals 0. Okay, and then you have a third equation that you can use to solve for the mu's and the x's, and that's the constraint, because so the constraint G2x equal to 0 gives us that 3x1, because we are assuming that the second one is active, right? So 3x1 plus x2 minus 6 is equal to 0. Now these three equations you can solve. They are linear equations. They can be solved quite easily. If you don't want to, in one of the homework problems there, it's complicated to solve these linear equations. You can always use the MATLAB function. What's it called? The symbolic package in MATLAB to do it, or Mathematica, or is there websites that can solve symbolic things for you. So you can get, in this case, this was not that hard to solve. So this is actually 2/5. I didn't want to put the details down here because this is not a course on solving linear equations, right? So you get those as the answers. X1 is 2/5, x2 is 24 by 5, mu2 is minus 2 over 5. Anyone recognize something wrong with this solution?
mu2 is negative.
Mu2 is negative. So mu2 is negative and not allowed, right? Inequality. We just showed that mu2 has to be non-negative. Okay. So this solution is invalid as well. Okay, let me move on. We'll make the first one active and the second one inactive. So now mu2 is 0 for sure, and so mu1 we need to put in the equations to solve. So again, the gradient equations can be written easily. The gradient of G1 had components 2x1 and 2x2, so that gets multiplied by mu1 and setting it equal to 0. And then the constraint, this we're assuming that the first one is active, so G1x is equal to 0, but that gives us that this x1 squared plus x2 squared equal to 5. So now we have three equations. But these three equations, they're not linear equations anymore because this is a nonlinear thing. So this is actually quite hard to solve. Okay. Yeah, so in fact, what you end up getting in this case is three, I believe, three possible solutions for x1, x2, and mu1. Okay, and you can solve them on MATLAB, which is what I did. Okay, but two of the solutions are actually complex valued, so you can just look at real valued solutions. If you look at the real value solution, that turns out to be quite have a simple form in this example. Okay. Actually, this is an exercise from one of your reference books, the one by Lowenberger and you. And so that's why they made sure that the answer was nice. Okay, just chose the coefficient so that, beforehand you can't tell that you're going to have a nice solution to these equations when you throw in quadratics like that. Okay, so so you get that as the only real valued solution. Okay. Now this solution seems promising. First of all, mu1 is equal to 1, so it's not negative at least. Okay. So now we need to check and the complementary slackness conditions are obviously satisfied. Mu2 is 0, and mu1 times g1 is 0, obviously, because g1 is 0 in this setting. And we can actually check. Of course, I mean, g1 equal to 0 was used in solving for these things. So obviously, if you check that, you'll get that it's 1 plus 4 minus 5, x1 squared plus x2 squared minus 5 is 0. And then 3x1 will be 3 plus 2 minus 6 is minus 1, which is negative, which also makes sense, right? So the constraints are met, and the second constraint is actually not active because G2 is less than 0. Okay. So this solution for X star is consistent with the KKT conditions. So you get that X star equal 1, 2, and mu equals 1, 0 satisfy the KKT conditions. Now you can check for regularity to make sure everything's okay, and that's not hard to see because now we know that the second constraint is inactive, and so we just need to look at the gradient of G1, but the gradient of G1 at X star is a non-zero vector. So so you have the linear independence condition automatically satisfied. Okay, so X star is regular. So everything is okay with this case. Now we still have another case. So maybe there are other possible solutions for X star that can arise from the last case, which is that the first is active and the second is also active. So now the gradient condition, a gradient of L, will give us these two equations. Both mu1 and mu2 are in these equations. And then we have to have both the constraint equations itself. Both are active. So you have 4 equations and 4 unknown. And these are quadratics as nonlinear equations. Again, not trivial to solve on using your pencil paper, right? Or in my case, my iPad. So again, let's resort to MATLAB. Solve these 4 equations on MATLAB, and you get these as your solutions. Okay, x1, x2, mu1, mu2, like this. But notice that there's a mu1 here that's negative in this first solution. And then the second solution, mu1's positive, but mu2 is negative. Okay, so again, this solution is not valid because one of the mu's is negative in both solutions. Okay, so that's because of this one and this one. So the only candidate for a local minimum, right, is X star equal 1, 2. The question is that a local minimum or not? So we need to check a sufficiency condition. You have to be careful with with these things because first of all you could have situations where something that satisfies the conditions, it could be actually a stationary point on the boundary. Okay, so it may not be a local minimum. So to check for local, whether it's a local minimum or not, you really need to look at this second order sufficiency condition, or you need to argue by some other means, like through convexity. Okay. All right. So let's actually do the second order condition in this case first, and then we'll also look at another argument. Okay. So to check the second order, this is not that hard to do in this example, which is why let's do the second order condition. So here we'll take the Hessian of L, and the Hessian of L is just the Hessian of F plus mu1 is 1 times the Hessian of G1 at X star. And those are not that hard to compute. So they had the 4x1, that'll produce a 4 on the left diagonal, and 2 here off diagonal. You get that. And then so again, if you look at the gradient equations, so for the gradient, where's the G, where's this one? This one here. So the gradient, has 4 here. Let's take another derivative, you get 4. The cross will give me a 2, and then this will give me a 2. And then the gradient, if you take another derivative here, you get 2 there, and the 0 on the diagonals for the G, right? So this is easy to compute. 2, 0, 0, 2. Is it? No, sorry, is it 2? Yeah, it's 2, right? It was 2, yeah, that's right, it's 2. So if you add these two up, you get 6, 4, 2, 2, which is easy to see that it's a positive definite matrix. Why? Because, why is this a positive definite matrix?
It's leading principal minus or greater than 0.
Yeah, the leading principal minus or greater than 0. So this one's greater than 0, and then the determinant of this whole matrix is clearly greater than 0. All right, so and if you look at the active constraint, it has a mu1 that's strictly positive. That was the other condition we need for sufficiency. Let's go back and look at that result again. So for the sufficient condition, we need the active constraint to have strictly positive, and then this matrix, this has to be strictly positive, but for y not equal to 0, but that's going to hold always if this is a positive definite matrix. So we don't have to check these conditions. Okay. So this means that X star is a local minimum. And now the constraint set is compact. Why is the constraint set compact? These are both the inequality constraints, right? Right. So this constraint set is compact, right? It's closed and bounded. Because x1 and x2 are not allowed to go outside the ball of radius square root of 5. This constraint, well, that I could actually make one of these guys go to minus infinity and still satisfy the constraint, right? So I can't conclude compactness of this set. It's just closed. But the overall constraint is the intersection of these two sets, right? So the intersection of these two sets has to be compact, even if one of them is compact. Right? Or I should say, the intersection of these two sets is going to be bounded if one of them is bounded. And since both of them are closed, the intersection is also closed. And so the intersection of these two sets is closed and bounded, so it's compact. So you have a set, a constraint set that's compact. That means F achieves its global minimum, right, by Weierstrass's theorem. It's a continuous function on a compact set. And so there's only one candidate for a local min, and that has to be the global min. Another way to look at it is if you look at just F itself, the Hessian of F is 4, 2, 2, 2, which is positive definite. And the constraint set is convex and closed. So in this special example, constraint set is convex and closed. And why is it convex? And we know it's closed already. Why is this constraint set convex? Well, you look at this set, right? This is a convex function being bounded by 5, and we proved somewhere early on, maybe in homework 1, that this set would be a convex set. Okay, same here. It's a linear function bounded by something. This is a convex function, special case of a convex function. So intersection of these things is a convex set. And so we get that the constraint set is convex and closed. So the first order necessary conditions is enough for X star to be a global min. We know for convex functions, first order necessary condition is enough for a global min. In this case, F is strictly convex, so it's actually a unique global min, but we knew that from our calculations. Okay. Any questions about this example? Pretty complicated, huh? Much more complicated than the equality constraint version. So in your next homework, I'll make you do a couple of these so you get comfortable. Okay, working with these. But the KKT conditions are more useful not for actually finding numerical solutions to these kinds of problems, but more importantly, the necessary conditions establish some properties of optimal solutions that can be used in other analysis. So that's typically how the KKT conditions are used. Okay, and those of you who are taking this course for 4 hours, in your project, I want you to look at some possible applications of optimization techniques that you learned in the course. So you can look at some papers and report on that. And so you'll see that where when you use KKT conditions, you're not necessarily going to be using them to explicitly solve an optimization problem, but to characterize some properties of the optimal solution that you can use in other parts of to prove other things. Okay, but more on that a little bit later. All right, so this is a good time for a short break before I do another example. So any questions before we take the break? Okay, 2 minutes. So we'll be back 11:49. All right. Okay, so any questions about the example they thought of during the break? Okay, so let's actually talk about one of the applications we discussed in lecture 2. So remember this power allocation problem, right? So so you have a transmitter, a receiver. It's a communication problem. You have a certain number of channels on which you're sending this information. Each channel has some noise power associated with it, and you want to maximize the bit rate of transmission across these channels, which is the sum of the log of 1 plus the signal to noise ratio, the power divided by the noise. And the constraint is that there is a total amount of power that you can use at the transmitter, and this power is non-negative. So this is a constraint, inequality constraint optimization problem. Okay. So let's write it in the notation of our class now, of the KKT theorem. Okay, so we assume that we have a total power, say P, that's available at the transmitter. Xi, that's the variable I want to optimize over, is the power allocated to channel I. Sigma I squared, noise power, and power is always positive or or non-negative because you have zero power, I guess. And so that's except for actually in the case of noise power, we'll assume that it's always positive. Okay. Strictly positive. Okay, and the number of bits that you can carry on channel I, this is given by actually what's called Shannon's capacity formula, but you don't need to know where it's coming from. It's a log of the signal to noise ratio, the signal power divided by the noise by 1 plus that. Okay, and the goal is to maximize the total number of bits I can send to these n channels. Okay, n is also the dimension of the vector x, which I'm trying to optimize. That's consistent with our notation. And I want to maximize this subject to these constraints. So this is a maximization problem, not a minimization problem. So the first thing I'll do is change the sign of the function so that I get a minimization problem. Okay, so I can apply the results that we have derived so far. So we have fx for our problem is a negative of this log. So it's a negative . Okay, and the constraints are that xi is non-negative, so gi of x is minus xi. So xi being bigger than or equal to 0 is minus xi less than or equal to 0. So, and the last constraint, this guy here, rather than calling it n plus one constraints, it's I'm going to call it the 0th constraint. So I'll let my I go from 0 to n in this example. Okay. Sorry. This is one. This is one. That's the 0th constraint. G0 is a summation of xi minus b. So we end up with a minimization problem in the form that we are used to. So does anyone see a problem with this in terms of finding regular solutions? Remember, x is n, has dimension n, and how many constraints are there?
N plus 1.
N plus 1. So can we have n plus 1 gradients that are linearly independent if they're n-dimensional? No. So, but it's okay with inequality constraint problems. Why is that? Because some of these constraints may not be active. So as long as we have n or fewer constraints that are active, I can still find a regular x. Okay, so let's not worry about that right now, and we'll check at the end to make sure that any solution that we find here is actually regular. Okay, so now let's look at the Lagrangian for this. So Lagrangian for this is negative . And I have the mu i's associated with these n constraints. And then I have what's called the last one, mu zero corresponding to the constraint that the sum has to be less than p. So that's my Lagrangian. Okay. Let's write the KKT conditions. The KKT conditions, of course, we have to have that the mu I have to be non-negative. Mu I xi has to be 0. This is complementary slackness for the first n conditions, right? Actually, it's mu I times minus xi, but that's the same as saying mu I times xi equal to 0. This is the complementary slackness, CS. And there's also a last complementary slackness condition saying that mu 0 times the function, the last function, g0. This must equal 0 as well. So complementary slackness. Okay, so and then we have the gradient condition. So the gradient being equal to 0 for L, and take the gradient. Okay, so I can't move this thing. Okay, there we go. Okay, so gradient of this function, it'll give me 1 divided by this with a minus sign outside, and then the derivative of this with respect to xi will give me another 1 over 1 sigma squared. The gradients of these guys will just give me a mu I here and then a mu 0 from this sum. Okay, so let's write all that down. So it's 1 over 1 plus xi divided by sigma I squared times 1 over sigma I squared, then minus mu I plus mu 0 equal to 0. And this holds for I equal to 1 to n. Right? Those you get n conditions for each component of the gradient. So, but notice in this problem, the xi's only appear in the ith equation. So there is some structure here that I can exploit to actually not have to consider, all 2 to the n cases. Okay, or which ones are going to be active, which ones are not going to be active. This makes the problem slightly simpler, as we'll see. Okay, so first of all, this equation, when I solve it, this implies that mu I, if I rewrite it essentially, is mu 0 minus 1 divided by sigma I squared plus xi for I equal to 1 to n. Okay. Remember, sigma I squared is strictly positive, right? It's a variance for noise, strictly positive. So mu I, we know from this condition here, mu I is non-negative, but mu I is non-negative. If I put that in here, that means that this quantity is non-negative. So I'll rewrite that as mu 0 is bigger than or equal to but the xi's are all, so this guy is strictly, these guys are strictly positive and these guys are not negative. So if I look at this whole quantity, this whole quantity is actually going to be, and so because sigma i's are also assumed to be finite. Okay, so this whole quantity is going to be bigger than 0. Okay, so what does that mean? That means you automatically have that the sum constraint has to be active by complementary slackness, right? So you go back to this equation, if mu0 is positive, that means this has to be equal to 0. Does this make sense from an intuitive viewpoint? So the sum constraint has to be active. Okay, let's see why that makes sense. If you think about it, I'm trying to maximize this function. I'm trying to maximize this function under a constraint on the powers. But if you look at this log function, that's monotonically increasing in the xi's. So if I left some gap in this constraint, I could fill up the gap by increasing one of those xi's and making the value of the function larger. So that means I shouldn't be leaving a gap if I want to maximize. Make sense? Okay. So that's why that constraint being active makes sense. Okay. But the other constraints may or may not be active. Let's see what happens with the other values of mu I. So we know that mu0 has to be positive. All right. So suppose for one of these other guys is active. So if mu I is positive for one of these other guys. Well, for those other constraints, mu I being positive by complementary slackness means that xi is 0. But plugging in xi equal to 0 in the gradient equation, in this equation, if I plug in xi equal to 0, I get mu I as mu0 minus 1 over sigma I squared. Which is strictly positive by our assumption. This means that mu0 is bigger than 1 over sigma I squared. So mu I positive implies that mu0 should be bigger than 1 over sigma I squared, or 1 over mu0 should be less than sigma I squared. So let's go the other way. So if I have if mu I positive implies that 1 over mu0 is less than sigma I squared, if 1 over mu0 is bigger than or equal to sigma I squared, that means mu I is going to be 0. So it's just reversing. Right? If A implies B, then not B implies not A. So if it's greater than or equal to this, then that means mu I is 0, which means that mu0 is 1 over sigma I squared plus xi. Which means that if I solve for xi is 1 over mu I minus sigma I squared. So the solution to these equations should be of the form, although we need to verify it, but it should be of the form xi equal 1 over mu I minus sigma, 1 over mu0, not mu I. Should be of the form 1 over mu0 minus sigma I squared. But of course, that's if xi is positive, right? If xi is positive. But if xi is 0, xi can be 0 too. And that happens when 1 over mu0 is less than sigma I squared. So you can think of the solution to these equations is going to be of the form 1 over mu 0 minus sigma I squared, the positive part. So what that means is that if 1 over mu 0 is less than sigma I squared, then xi star will be 0. If it's bigger, then it's equal to that value. So that's what the positive part means. Or it can be written as max of 0 and 1 over so in other words, if this guy is positive or non-negative, I guess, then xi star is equal to that value. But if it's negative, it's going to be 0. Okay, so that's what we get from solving these equations. So this mu 0 is still a variable that we need to determine, but we have enough information to do that we get from our equality, from our active constraint. So basically, we have the solution to this problem as xi star equal to this. Well, at least this is you can think of it as a guess for the solution, because we still need to make sure that it satisfies the complementary slackness condition, okay, which we'll do that in just a second. But the solution is given by this, where we know that this total power, this constraint has to be met with equality. The total power has to equal P, so that will actually allow us to solve for the mu 0. So the way I would solve this problem for x star is first, okay, given the sigma i's, I need to find a value of mu 0 such that when I sum up these quantities, I get P. Okay, and that'll give me the value of mu 0. So what I essentially do is keep increasing 1 over mu 0, right, until I hit the level P for the sum. And this is called a water filling solution. So it's an interpretation for the solution, which you can read up in books on communication over parallel channels. I'm not going to go over that interpretation in this class, but you can think of this. So you just keep increasing this level 1 over mu 0 until you hit P for the sum. That's the value of mu 0 that satisfies the equality. Plug that into here to get the xi stars. Okay, so now let's do one last thing to check to make sure that the xi star was essentially derived from the equations, but then at one point, essentially, we could go one way. If this is true, this is true, but the other way, when xi equal to 0 implied this, but this doesn't necessarily mean that xi will be 0. So we need to check that complementary slackness condition separately, which we can do. Okay, so let's look at what happens when xi star equal to 0. Then 1 over mu 0 minus sigma I squared from our equation has to be less than or equal to 0, which means that mu I has to be mu 0 minus 1 over sigma I squared, which says that mu I has to be greater than or equal to 0. Now, if xi is, so the product of xi star and mu I will be 0. Similarly, if xi star is positive, then xi star is 1 over mu 0 minus sigma I squared from our previous equations, from the Lagrangian condition. And so we get that this is mu 0 minus 1 over sigma I squared plus xi star, just rewriting that equation. But that's equal to mu 0 minus mu 0, which is equal to 0. Okay. So xi star is times mu I is equal to 0. So we basically get the complementary slackness conditions. Right. All right. So so basically, so we showed that the solution to this problem on this constraint set is, okay, well, we showed that X star is a candidate for a local minimum, at least. That's what we have shown, right, through the KKT conditions. Now, this function f, if you look at this function, what kind of function is this? It's a log, it's a negative log, right, of the xi's. So negative log of something, log is a concave function. The negative log will be a convex function. You can check using derivatives if you want to, but it's, you know this, right? It's a convex function. Constraint set, this we also know is convex, right? This constraint set is convex. Okay. Again, you can verify that constraint. If you want to verify quickly, just take alpha times some x1 in the constraint set plus alpha, so alpha times say x and 1 minus alpha times y, and you can verify that that will also, if each of the if x and y satisfies these constraints, then alpha x plus 1 minus alpha y will also satisfy the constraint. So this is not hard to see that this is convex. This is like what's called a probability simplex constraint. Okay, except that a probability simplex, you have one here. Here you have actually with equality, but anyway, it's a convex set. So X star is a solution, is a local minimum for a convex function over a convex set. So it must be the global minimum. There's only one candidate, and it has to be the global minimum. So then if you convert f back to the original function by changing the sign, so we say that X star maximizes, it gives you the maximum rate on these constraints. Okay. Now the one question remains, is X star regular? So I said we have more constraints than n, but can we have more than n active constraints? That's the question. So we know one of the constraints is active, the one corresponding to the sum. Now I claim that not all the remaining constraints can be active. Why? What will happen if all the remaining constraints are active? What would that say about the xi's? So we know that this constraint, this constraint is active. So G0 x star equal to 0. But what about these guys? Can they all be active?
No, because then they would all be 0, and then you can't have the sum equal.
Right, so they can't all be 0, because if they were all 0, then the last constraint wouldn't be active. Right, so at least one of those constraints has to be inactive. So you'd be, what this says is that you have to at least allocate power to one of the channels. Right? And so that's why we have this condition hold. Okay. Yeah, so the answer to that is yes. So we're done. That's the solution to the problem. Any questions? Okay.
How are we concluding x star is regular?
Oh yeah, because basically these gradients are going to be linearly independent, right? So if you look at the gradients of the GIs, so that's actually a good question. Maybe I skipped a little beyond. So if you look at the gradient of the GIs, all right? So these will be like 0, 0, 0 with a -1 in the ith component, right? So that's the only xi. That's the only thing that's non-zero. And then if you look at the gradient of G0, that's 1, 1, 1, 1, right? So clearly, if all these guys, if all these guys were active, then you know then what would happen is that this vector is going to be a linear combination of all the GIs, gradient of GIs. So you won't have X be regular. But as long as one of these guys is inactive, then if you take the linear combination of these, then these vectors will have one of these guys will be missing, and so now the remaining ones are going to be linearly independent. Okay. Yeah, I skipped that detail there, but that's a good question. Any other questions? So a lot of times with when you try and solve an optimization problem analytically using KKT conditions, you might be able to guess the answer first, right? So in fact, in this particular example, you might be able to guess, and if you had good intuition for the problem, you might be able to actually guess that the xi star should be of this form. Okay, once you do that, then all you have to do is check that xi star satisfies the KKT conditions, necessary conditions. Okay, and then you know that, and then of course then you can use convexity or whatever to conclude that it's a global minimum. Okay, so that's the approach that actually, if you look at communications textbooks, they'll give you the answer first and then say, okay, the answer satisfies the KKT conditions. But since this is an optimization class, I thought I should go the other way, which is to actually try and first establish why that should be the right answer, and then check the KKT. Okay. Okay, one last thing before we go, because this is going to be on your homework assignment, is that we gave a sufficiency condition last class for, remember this sufficiency condition? This one? Okay. This is for an optimization problem where you just have those linear, it's equality and inequality constraints. So there's actually a slightly more general version of the sufficiency condition, where in addition to these equality and inequality constraints, you have some additional constraints here. Now these may or may not come from equality or inequality constraints. There could be some arbitrary constraints, right, on X. Okay. Now, so the result, it says that you could still apply the Lagrangian to get some interesting solutions to this problem. And the way you do that is first define the Lagrangian in the same way, sorry, as before. Okay. And then check this, check to see if there exists x star, lambda, and mu that satisfy the constraints. So they're feasible. X star is feasible. And then these are the KKT conditions. So mu j has to be non-negative and the complementary slackness condition. So if these satisfy this, and in addition to that, if I look at the Lagrangian function at that x star, and for this choice of lambda and mu, if that turns out to be the one that minimizes the Lagrangian for that lambda and mu over x belonging to S, then so this is a global minimum for this Lagrangian. Okay, so if that turns out to be the case, then x star is a global minimum for this optimization problem. Okay, so this is a condition that one can check, and actually, so in some applications, it, you know, when you may have, in addition to the these constraints, inequality constraints, you could have some other constraints that aren't necessarily captured this way. Then you could, as long as you can solve for this equation easily, right? And maybe you can in some cases. Then you can also use the KKT conditions to get a solution to the original problem. Okay. Now it's actually not very hard to prove this, and I'm going to leave the proof for your homework. But I'll give you all the steps. So it'll be a proof, but basically I'll say, well, first show this, then show this, then show this. Okay, so that it's easy for you to carry out the steps. But I wanted to actually state the result here. And actually, we're going to use this result in the next class. At least I hope to do that on Tuesday, to give you an alternative way to solve this optimization problem, the one that we just solved. Okay, just to illustrate why that other sufficiency condition might be useful. Okay, so that's the plan, and I guess I'll see you guys next Tuesday. Now, next Thursday, there's not going to be a class because I have an NSF panel to be on. So I'm going to be busy both Thursday and Friday next week. So so there'll only be one lecture next week, and then your next homework will be due, the Tuesday after next, so a week from the coming Tuesday, and that will cover inequality constraints, okay, and KKT conditions. Oh, I'm out of time. 12:22. Okay. Any last minute burning questions before we end?
Can you give an example of a non-equality or inequality constraint?
Something that's not an non-equality constraint. Yeah. Well, you can't. Well, it depends. I mean, it's some set that you can't write as a function being less than something, but we'll have to cook that up. You have to make a kind of a strange surface to make it not a. Let me think about it, and I'll give it to you in the next class. You can imagine creating even actually convex sets that are not really bound by inequality constraints, right? If you design your set properly, I mean, so you can't capture it with inequality constraints. Yeah, but that's a good question. So a specific example.
Can it be like x should be an odd number or something like that?
Yeah. Oh, I don't know about that. Yeah. Okay. All right. So talk to you guys next week. Actually, that might be a good exercise for you guys to work out. So come up with an example of a set that cannot be captured by inequality constraints.